Hello. In this problem, air is given as a mixture of oxygen and nitrogen by mass. And we are to determine mass and mole fraction of each component. Of course, mass fraction is almost obvious. We don't need a test step to evaluate that. 23% by mass, that means X of oxygen must be 0.23. That's the definition of mass fraction, and nitrogen mass fraction must be 0.77. We have to find the mole fraction and the molar mass of air, and then let this air occupy a state with 1000 kPa and 1000 Kelvin pressure and temperature, and we have to find partial pressure of each component. So let's use a test step, a suitable test step for this purpose. So we are going to use, I already logged in, we are going to evaluate state, a system state, and we are going to use a general mixture model, let's say an NPG or NIG model. Okay, let's use the mixture of perfect gases. NPG means any n number of gases are allowed in this case. As you can see, in addition to the state and graphics and I/O panel that you see in every test step, this one offers a composition panel, and any number of gases can be selected for the mixture. So we will select air as a composition is given in this problem, oxygen and nitrogen by mass. Oxygen is given as 23% and nitrogen is given as 77%. We add, and the air mixture is produced here, but this is given in molar terms. As you can see, already the mole fraction is calculated. So the answers are right here. The mole fraction is, as you can see, is Y, 0.207 and 0.79 for nitrogen, and these are the mass fraction that I entered, and this is the mole fraction pictorially shown here, and the composition is also shown here in terms of mole. Okay, the second question. And as you can see, as you add mass, it's already shown here about the mixture A. So to take a mass out, you can select that and say remove that, or you can remove this one by one or add them one by one if you want. 77 kg of or percent, up to you. If you add that, and oxygen would be 23, add that. As you can see, as you're adding, the mixture is updated. The mixture molar mass is 28.84 kg per kilomole, the mass divided by mole. Okay, so let's go and evaluate the state. Recall that the state it occupies a 3 meter cube of volume, and the values of pressure and temperature are given. Volume is 3 meter cube, and already the mixture A is our air mixture, state 1, 100 kPa, no, 1000 kPa and 1000 Kelvin. So the mixture is calculated. As you can see, the partial pressure is shown here, 207 and 792. Of course, it will be simply 1000 kPa times the mole fractions. And all other partial properties are also tabulated here, which are covered in chapter 14 in your textbook, and chapter 11 and 14. All right, I'll just stop here. This is rather really simple problem. You can do so many things. You can evaluate another state, for instance, with air, or you can change the composition by adding more things. And of course, everything else like superprint will print out, the details about the mixture. Mixture A is made of this and this, and the state that we evaluated plus the test code. So everything else is same as any other test step, except we have the working fluid is composed here as a gas mixture, and we can make as many working fluid as we want, mixture A, mixture B, mixture C, and so you can see the possibilities, and we'll solve a little more exciting problem in the next example.